Hello again. So this is joint work with Ludwig Schmidt. So this is a very long title, so let me start parsing it. So mixtures of Gaussians are a very popular way of modeling multiple populations. We've already seen some talks at this COLT. But intuitively, suppose you have some attribute, and you're drawing from not just one population, but multiple populations. And you kind of model each single population. This attribute kind of follows some Gaussian distribution. But now you're drawing from a kind of a mixture of these populations, so naturally your overall distribution is a mixture of these Gaussians. And so formally, a KGMM is just a distribution with PDF, a mix with mixing weights W of some Gaussians with means mu I and sigma and variance sigma I squared. So they kind of look like this. Okay? So the high-level goal of this paper is given samples from this KGMM, just learn the distribution. Okay, simple enough, sort of. I mean, what does it mean, I guess the question is, to learn a GMM? So the most desirable goal, arguably, is parameter learning, which is to recover the underlying mixing weights, means, and variances. Okay? A somewhat weaker goal is something called proper learning, where the goal is to return some other KGMM, which is close to the underlying GMM in TV distance, also known as statistical or L1 distance, or other metrics such as KL or whatever. But in this talk, we'll focus on TV. Another goal, even weaker, is something called density estimation, where the goal is to just return anything, not even a KGMM, which is close to the original in TV distance. So in this talk, we're going to focus on proper learning, and I want to take a brief aside to motivate why that might be a reasonable thing to do. So as I mentioned before, parameter learning is arguably the most desirable, right? You actually recover the parameters of the original populations that you wanted to model. Unfortunately, for KGMMs, it just takes too many samples. And this is well known. So a paper by Moritz Hart and Eric Price showed that even for a mixture of two GMMs, you need 1 over epsilon to the 12th samples to recover the parameters. And in general, you need 1 over epsilon to the 6k minus 2 samples for a mixture of k Gaussians. And this is like, even for epsilon reasonable, this is prohibitively too many samples. So in general, it just seems hard to do parameter learning. On the other kind of side of the spectrum, density estimation, it turns out, can be done much with fewer samples and also very efficiently, computationally speaking. But it's just kind of unsatisfactory because it lacks interpretability, right? Just you get some blob, which is close in TV distance. Sometimes that suffices. Sometimes it's just kind of unsatisfying. So the goal of proper learning is to hopefully combine the gains from density estimation in that it's from parameter learning in that it's interpretable, but while being like sample efficient. And in this talk, we show it's also computationally efficient, at least in some regimes. Okay? So here's a very big slide of kind of the previous results and kind of our results in context. Is there Okay, so again, for parameter learning, we get these rates which are 1 over epsilon to the theta of k. So they scale in this kind of very exponential way, and particularly if k equals 2, you already have 1 over epsilon to the 12th samples. To contrast, for density estimation, the sample complexity is much better. It's k over epsilon squared, which is like much better, obviously. And moreover, the time complexity is also great. In a recent paper, joint with Jaydev Acharya, Elias Diakonikoulos, and Ludwig Schmidt again, we showed that there's an algorithm which runs in time which is linear or nearly linear in the number of samples we take. So in some sense, density estimation of KGMMs, at least in one dimension, is more or less solved because there's an algorithm which is simultaneously sample optimal and nearly linear time. But what is the state of affairs in proper learning? Well, the previous results before, the sample complexity again was optimal up to these log factors of k over epsilon squared, which is again much better than the rate for parameter learning. But the run times were not so great. So the best run times were due to Kostis and Gautam Kamath and Acharya et al. And their rates were 1 over epsilon to the 3k minus 1. So again, this runtime is has this kind of 1 over epsilon to the theta of k behavior, which is quite undesirable. Our main result is an algorithm, in particular, notice, that even for k equals 2, this runtime is like 1 over epsilon to the 5th. So this is not nearly linear time in any regime. In contrast, our results are we get nearly sample optimal algorithms that for k equals 2 run in nearly linear time. And in general k, they get this weird runtime. But the point is, our algorithms are always nearly sample optimal, And as long as k is constant, this term vanishes, and our algorithm runs in nearly linear time. So we get nearly linear time algorithms for constant k. Okay? So how do we do this? So our starting point is the density estimation algorithm I mentioned previously, which formally says this. There's an algorithm which takes this many samples from a KGMM and outputs specifically an O of k piecewise polynomial where each polynomial has degree log 1 of epsilon, such that the L1 or TV distance between the output P and the original distribution is less than epsilon with high probability. And moreover, this algorithm runs in nearly linear time. In other words, given these samples for free, we can get this density estimate without any cost in either sample or runtime. And now all we need to do is a purely algorithmic problem of finding the best KGMM fit to this O of k piecewise polynomial P that we've already output. Okay? So how do we do this? This is kind of a nasty problem because mixtures of Gaussians aren't very nice to work with optimization-wise. Our main tool will be this thing called systems of polynomial inequalities. So you might not be familiar with systems of polynomial inequalities, but hopefully you're at least somewhat familiar with something called totally quantified Boolean formulas, which are more or less things of this form, where you have Q, which is, there exists x1 for all x2, there exists s3, so on and so forth, B of y, comma x1, xv, where y are free variables, and these x's are the variables you quantified over. Okay? So this is just some sort of, so this Q is satisfiable if there's some y which satisfies this. Okay? So hopefully this makes sense. A system of polynomial inequalities is just kind of like the real valued equivalent of this. So now you replace this B with a P, where P is a logical combination of polynomial inequalities. So, a certain polynomial is greater than 5, and another polynomial is less than 5, or another polynomial is less than 2, or whatever. And now you're quantifying still over these x's, but they're real valued. And the free variables are also real valued. And that's it. Okay, and this has very rich theory, known as the first order theory of the reals. I won't delve into that very much. I will just use this theorem from the field, which says that if this P has m constraints and the polynomials in P have degree at most d, then you can find a solution to Q, if one exists, in time number of constraints times degree of the polynomials to the number of free variables times 2 to the number of levels of quantization times the product of the number of variables you're quantifying over in every level of quantification. So it's some weird runtime. It's not super important what this is. The point is that there is a way to do this. And what we're going to do is we're going to somehow set up a system of polynomial inequalities which allows us to do this sufficiently. Okay, our system of polynomial inequalities will have O of k free variables, one for each weight, mean, and variance. It will have 2 levels of quantification. Each has O of k variables. And it will have a polynomial formula with max degree log 1 over epsilon and k terms, so O of k terms. And if you just plug this into Rennegar's algorithm, you will get actually a slightly better runtime than I promised, but that's because I'm lying and I'm hiding some stuff that you don't need to see. But morally, this is what's going on. Okay, so let me kind of really briefly tell you what's the high-level ideas of how to do this. So again, we have a given O of k piecewise polynomial of degree log 1 over epsilon. We don't find a KGMM which approximately minimizes the TV distance to P. How do we do this? Well, the first problem is KGMMs aren't polynomials. So what we can do is we can just approximate each polynomial by a 3-piece piecewise polynomial of degree log 1 over epsilon, just like a truncated Gaussian, a Taylor expansion. And now we have everything's like piecewise polynomials at least. So how do we encode L1 distance between P and a mixture of these shape-restricted polynomials? Well, if we know where the breakpoints of the polynomials are, of all the piecewise polynomials, then the difference in each piece is just the L1 distance between 2 polynomials. So we can use a one-level quantification to guess where the breakpoints are. And to encode L1 distance between 2 polynomials, if you think about it, if you know where the zero crossings of the polynomials are, then within each interval, this is just like a regular interval, or integral. And so after you do this, if you quantify over to guess where the zero crossings of the polynomials are, the rest is a polynomial equation again. Okay, and if you do this and with some other steps that again skipped, you get our algorithm. And one lie that I want to just briefly touch on is instead of encoding a k distance, or L1 distance, sorry, this is actually impossible for us with getting the right kind of runtimes we want. We have to do something else. We have to encode a k distance, which I won't even define. But more or less, we're just going to use the k most significant zero crossings of h minus g. And this still works and allows us to get the runtimes we asked for. So I'm out of time, so I'll just flash this last slide in. Thank you for your time.
So maybe a quick question for Jerry while this next speaker is setting up.
So the question was, do we only use existential quantifiers? And I think in our algorithm we actually use both. Yeah.
From what you showed, it seemed like it was a existential.
Right, that's because I was lying.